Conservation of energy. And I will say, for a long time, forces used to be my favorite topic in physics. But the older I get, the more I'm starting to realize conservation of energy is just so much cooler. It makes our lives a lot easier. And it pretty much has all the power of forces except, some extra oomph that is going to really push it to like the next level of physics. And so if we were to kind of explain what conservation of energy is, it pretty much comes down to this. If I have like a ball on a table, for instance, like here's my table. If I have a ball on my table at a height h above the ground, that ball has what is called potential energy. And anything with a height off the ground has potential energy. One thing that's interesting about height off the ground, well, ground is a relative term, and here's what I mean by that. Ground could mean, the ground that you're currently standing on right now. It could also mean if you're at like a 10-story tall building, then you could say the ground is actually like the physical ground, the earth. If you want to talk about ground as sea level, like you're 1,000 feet above sea level, you can do it that way. But pretty much you should always define ground before you start any energy problem in physics. And almost every time it's just whatever the floor happens to be is going to be your ground for that problem. And so any object above the ground is simply going to have potential energy. And let's say this ball falls and is heading towards the ground with some velocity v. As soon as that ball's moving, the potential energy is going to be starting to get converted to kinetic energy. And kinetic energy just means the object is moving. So potential energy, the object has height, like off the ground. And for kinetic energy, the object has velocity. It's moving. And that velocity can be positive or negative. It doesn't matter. It will have kinetic energy either way. And it's possible for it to have both kinetic and potential energy. Like, for instance, when the ball is like halfway in between the ground and the table and it's starting to move with a little velocity, little v, we can call it, then that also is going to have a combination of potential and kinetic energy. But the cool thing is, at every point, as this ball falls off the table and ultimately hits the ground, the energy in the system is going to be the same. In other words, the potential energy of the ball on the table is equal to the kinetic energy when it's at the bottom. If we were to explain that in terms of an equation, this is what it would look like. First of all, we have the definition of potential energy. So I've seen a couple symbols for potential energy. I've seen PE, I've seen U, capital U. Either way, it's going to be equal to mgh, the mass of your object times the acceleration of gravity, which is 9.8 or 10, we can round up, times the height that you're above the ground. And again, the ground is a relative term. And so then we have kinetic energy, and kinetic energy can be Ke. I've also seen it as just K, but either way, that's going to equal 1/2 mv squared. Probably one of the most famous equations in all of physics is these two equations right here. And this one says the kinetic energy in an object is equal to 1/2 times the object's mass times its velocity squared. An interesting thing about the velocity squared term is that let's say you have a negative velocity. Well, if you have any negative number, -2, -5, -1, whatever, two negative numbers multiplied by each other because it's squared is always going to be a positive number. In other words, the kinetic energy in your system is always positive. Or 0. It can be 0 as well. So it's always a positive number or it's 0. Potential energy, you actually can have a negative height, which is a really weird thing to say. But looking back at the table example, what if we define the table as having 0 height? If the table, then you consider 0 height, my ground, then when it falls below the table, you can actually have negative height, which is a really weird concept. But this number can be positive or negative. It really depends where you choose the ground to be. And then we can use these two definitions of energy to say, okay, well, the total energy in my system always stays the same as long as conservative forces are acting on my object. I can talk about that in a second. But the total energy at point 1, whatever point 1 happens to be, it could be on the table, for instance, is equal to the total energy in part 2. We can say part 2 is at the bottom. We can say it's in the middle. Here's an example. Part 1, location 1 is at the top. Location 2 is at the bottom. the energy at point 1 is equal to the energy at point 2, and that's because there's no external forces acting on this object. There's no friction. There's no guy pushing the ball. Well, I guess it has to maybe roll off or something in order for it to actually fall down. But assuming that no other forces are acting on this ball as it's falling, the energy in the object is going to be conserved. And conserved just means initial equals the final. Okay? And if we were to think about, well, what is energy total? The total energy in the system is equal to an object's potential energy plus its kinetic energy. So the sum of the two forms of energy is going to add up to equal the total. And so E total 1, we can say the potential energy at point 1 plus the kinetic energy at point 1 is equal to the potential energy at point 2, it's supposed to be a 2, plus the kinetic energy at point 2. So they're equal to each other. And I will say this, I've also seen this form of the equation. I just kind of want to throw this out there. I have seen this equation for definition of conservation of energy. I've seen delta potential energy plus delta kinetic energy is equal to 0. That's another way of saying the exact same thing, except I hate this definition because it's so confusing. We have the delta notation, which first of all no one understands. But what it's really saying is if we think of what delta means change, final minus initial. So I'm going to write it like that. Potential energy final minus potential energy initial. That we can consider like a quantity. Plus kinetic energy final minus kinetic energy initial. And again, that's some kind of quantity. And that's equal to 0. And if you don't mind, I'm going to add the negative terms to both sides. So I'm going to add PEI to both sides, the initial potential energy. I'm going to add the initial kinetic energy to both sides. And here's what I get with that. Potential energy final plus kinetic energy final on the left is equal to potential energy initial plus kinetic energy initial. And that should look very similar to what we've just seen a second ago. If you replace initial and final with point 1 and point 2, that's exactly what we're looking at here. The total, E total 2 in this case, you can mix and match, you can say it backwards, it doesn't matter, is equal to E total 1. The two energies are equal to each other. That's what conservation of energy says, okay? So you can write conservation of energy this way. Just know that 9 times out of 10, this equation is going to be more complicated than this equation. I like this equation a lot more. And now, one more thing. Let's talk about when energy is conserved. So,